I'm recording now. Good. So welcome. Good morning. So yesterday we talked about the plan stress and also the most importantly the stress representation. Okay, in advanced course we typically use one symbol for stress, sigma. Okay, and the subscript indicating the plan and the direction. And in this course, if we only see one value, one subscript, which means that they are repeated, okay, they are the plan and the direction are in the same direction, in the same along the same axis, okay. So sigma 1 1 2 2 3 3 actually means sigma x, sigma y, and sigma z. And in this course, we use tau to represent the shear stress, but actually this is kind of meaningless because when you see the subscript, which is different, which are different, x and y, or you can say 1 and 2, okay? Which means that the first one is plan or surface, and the other is the direction, which means that they are not parallel. The axis they along with it, they are not parallel. So which means that there must be a shear. There must be a shear, right? So that's you can see this is a shear stress to see the subscript. Okay. And we talk about plan stress, which is the most simplest case because there's no z components in this case. Okay. And then typically we will know the sigma x, sigma y, and tau xy. And we're going to, yesterday we talked about how to determine oblique inclined sections with arbitrary angle tilted. Okay. And we want to get the sigma x1 and tau x1 y1. Okay. And then we do a really typical proof, make the stress times its own area and become force, and then we can do the force equilibrium, and then we can get sigma x1, tau x1, y1, and we prefer this formulation because this is it will relate it to more circles. And then we introduce the stress invariant. Okay, sigma x plus sigma y will always equal to a constant. So you can simply get the sigma y1 if you know sigma x1 first. Okay, and then we done the first example that if we have this stress element, and then how about the stress element with the surface with the negative 15 degree, and then we just draw, we just substitute the formula and we can get this one. And then a sigma y1 can be used by can be determined by the stress invariant. However, I still encourage you to determine substitute the theta equal to minus 15 plus 90, because I will encourage you to determine new sigma x1, and new sigma x1 is actually the old axis y1. Okay, so you can determine the sigma x1, and then you can determine this is minus 1.4 MPa. And most importantly is this one. Okay, this one is kind of important because when you see that, when you determine that, you will determine this is positive 31.0 MPa, which is different from this negative 31.0 MPa. Maybe you think, oh, why they are the same, they are the same stress status, but why this is negative and this is a positive? Because the focus are different, the axes are different in these two cases. Okay, so if you choose this is new x1, new y1, and tau x1, y1 should be in positive direction. However, they are still in the same stress status, in the same stress element. Okay, so this is the key that I'm going to introduce yesterday. And then we talk about the principal stress. Principal stress means maxima or minima normal stress. Okay, and then we want to find the maxima minima of the formula, which is differentiated respected to the theta and then set into the 0. And the solution is this one. So which means that whenever theta satisfies this equation, and that theta implant, the theta surface will give you the maxima or minima stress. Okay, and then we found that the tangent to theta p can be plotted as looks like that. However, if we want to satisfy this equation, we will always have two solutions within this range, 0 and 2 pi range. Okay, so we will always have 2 pi solutions. And if we have tangent to theta, we can use the geometry effect, geometry conditions to obtain cosine 2 theta p and sine 2 theta p2. Okay, so we can obtain these two, and then we substitute to the formulation. We can get sigma x1 at that plane, which means that maxima or minima normal stress. And then this is the maxima or minima stress. We call that principal stresses, sigma 1 or sigma 2. 1 is the biggest one. The sigma 2 is the minimum. Okay, and then we notice that this is sigma average plus r, sigma average minus. Okay, and then it also satisfies stress invariant. And then we substitute the cosine and sine 2 theta p. We obtain when stress, principal stress occurred, there will be no shears on that, 0. Shear will be 0. And then we also introduce the maximum shear stresses, and we do exactly the same thing, differentiation. And then we found that tangent to theta s equal to this one. So whenever the theta satisfies this equation, that plane will give you the maximum shear stress. Okay, and then we compare the tangent to theta p, tangent to theta p and tangent to theta s, and we found that actually theta s and theta p can be correlated by you inverse the tangent to theta p and give the minus, and then you will have the tangent to theta s. Okay, so you can see that they are kind of they have the fixed relationship between each other. So I just try to plot the tangent x, and I do inversion, and I just give the minus sign to upside down again. And then we check these two red solid line. We found that the phase difference between these two cases are either shift forward half pi or backward half pi, which means that their differences are 45 degrees. Because now we talk about the figure talk about 2 theta p. The 2 theta p difference are 90 degree, right? 90 degree forward or backward. So which means that theta p is plus or minus 45. Okay, and then we do exactly the same thing for examination for the maximum shear stress. And then we notice that we obtain this sine 2 as theta s, cosine 2 theta s. And then we can get the tau mix is R. The tau mix is R. We talk about the value, okay? Later we will using the example to, we will use example to let you know how to determine the direction. Okay, so the summary is really important here. Maxima, average plus R, minima, average minus R, maxima shear stress, R itself. Okay, and tau mix is actually sigma 1 minus sigma 2 divided by 2. You can just sum them up together and then divide by 2. It will become R. Okay, and then yesterday we finished, we end at this procedure. So this is the problem, and then we are going to get the principal stresses. The principal stress tangent to theta p equal to this one. Okay, be careful about the sign for this. Okay, so you see 32 is downward, right? So this is minus 32, and sigma y is 30. Compression this is minus 30. So don't forget. Don't forget the negative sign for the compression and the shears. Okay. And then we obtain theta p equal to minus 14.7. You can determine this by pressing your calculator, okay? Arctangent, okay? Or tangent minus 1 function. You can get minus 14.7. Oh, be careful when you talk about using your calculator. Sometimes the unit in your calculator set as radian or degree. You need to set, okay? Maybe you should enter some setting and choose 1 or 2. 1 may be the degree, 2 may be the radian. Be careful about that. Otherwise, your value will be totally different. Okay, so 14.7 degree negative, and I just adding another theta p equal to plus 90, because you know that the triangle geometry will sweep by 180 degree, but it's 2 theta p, right? So plus 90. So plus 90, maybe you can do plus 90 or minus 90. But if I were you, I just make this one positive. It's simpler. Okay. So I don't know which one is the maximum. So I just give the we leave the empty, and then we will get the value, and then we can determine which one is the sigma 1 or sigma 2. So sigma p 14.7. So 27 plus 57 cosine. Oh, I substitute 75.3 times 2. So it's 150.6 first. And then we can continue. 32 sine 150.6 degree. And we get minus 3A.4 MPa. Okay, and the other we can get, which is sigma equal to 92.4 MPa. Okay, so it is clear that the first one is 2. The other is 1. So your theta P1 and theta P2, and this is theta P2, and this is theta P1. Okay? So that's how we determine 1 or 2, just based on the value. Okay? And then luckily we see sigma P1 is minus 14.7. So which means that we have a positive at that. Okay. And this is 92.4 MPa, and this is 92.4 4 MPa, and Sigma 2 is minus 38.4. And this is corresponding to 75.3 degree. So this is compression, and this is 38.4 MPa and 38.4 MPa. Okay, so Sigma 1, Sigma 2, done. Finished? Finished. Do we have shear stress when the principal stress occurred? No. So we don't need to bother to determine the shear. So shear stress will equal to 0 when principal stress occur. Okay. So no shear stress. Okay, when principal stress occurred, no shear stress need to be determined, because you can imagine that all the stress component contribute into sigma 1 and sigma 2. So no room for shear stress. Okay, so this is the first example. Well, first problem for this. And okay, then we are going to do the second one. Where's tau max? Tau max, we need to get to theta s, right? Theta s equal to theta p plus of minus 45, right? So theta s can be 30.3. I used minus 14.7 degree plus 45, so you get 30.3. And then we can have tau x1, y1. And if we substitute 30.3, it will become mix, right? So minus 84 minus 30 and 2. So sine 60.6 degree plus tau x1, xy times cosine 60.6 degree equal to minus 65.73 m pa. Okay, 65.33 m pa. So let's draw what will it look like. 30.3. So 30.3. 30.3 degree. Okay, and this is x, and this is x1. I'm sorry, I should move to the bump to this place. Okay, and so this is well the 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 okay, so this is a stress element. You see 30.3 degree plan will have minus 65.3 33 MPa. So it's downward, right? X1. In X1 plan, negative Y1 direction. So you will have 65.33 MPa. Again, we don't add minus sign when you draw the stress element, because you specify the direction by the arrow. Okay, and then now, because they are all occurred in group, so we can directly obtain the other three So they are 65.33 MPa. Okay. Right. Is that done? No, because when maximum shear stress occurred, still there are still some value for normal stress. Okay, so need to be careful. We need to determine sigma x1 84.3 minus 30 divided by 2 plus 84 plus 30 divided by 2 cosine 60.6 degree plus minus 32 sine 60.6 degree equal to 27 MPa. Okay, 27 MPa. 27 MPa. Right. So 27 MPa on the plan minus 30.3 degrees. Sorry, no minus. So positive 27. Positive 27 MPa. Okay. And the opposite side 27 MPa. Okay, is that done? No, because we still have y1 to determine, right? So sigma y1 equal to sigma x plus sigma y minus sigma x1 equal to 84 plus minus 30 minus 27 MPa. Okay, so that's it. 27 MPa is also positive. So positive 27 MPa. The other is 27 MPa. Okay, so that's it. Everything's done. Okay, that's the answer. I believe the concept is very straightforward. Okay, just make sure that you set correct angle and not be careful about the minus sign or positive sign, and that's it. And then I'm going to introduce a very important skill called Morse law. And don't be afraid. Morse law is a tool that can help you. Okay. It can help you to figure out the angle, the angle difference between the planes. The Morse law is really kind of illustration for you, schematic illustration for you. OK， 摩尔虽然是一个工具，它可以帮助你去了解每个角度之间的关系。哦，可以画成一个圆哦，非常的聪明。哦，它就是自然的就可以用一个圆去表达它。So, which means that the scientist or mathematician found that the relationship between each angle, each principal stress or shear stress, maximum shear stress, they have set, it can be represented by a circle. That's really interesting. So when sometimes when you figure out a theory, when the smart man, smart girl, they figure out a theory, and then you find that the theory can represented by another simple geometry problem, and then which means that yes, typically sometimes which means that you are right. So this is kind of interesting. 我说啊，就是当聪明的就是人呐、去想到说我猜测一个理论，就猜测一个理论，发现哎，我可以用一个简单的几何形状去表达它们的之间关系，那通常那就是对的。我觉得很神奇，就是我之前在英国念书的时候，我自己跟老板就讨论出，不知道叫做讨论出一个理论去解释，例如说形状记忆核心的微结构，它们之间的关系，就是结构如何稳定的关系。然后我就写到后来，我就把这式子给老师看，然后老师就说：“哎，这个不是一个封闭式的几何形态嘛？”然后我就看，哎，还真的，就把所有的微结构里面的 normal 放在一起，它就会组成一个封闭的形状。如果今天不就是例如说一个立方体或者一个长方体或者一个梯形的体，但如果今天那个材料不 compatible microstructure 不 compatible 的话，比较不稳定的话，这个几何会打开，你知道吗？它就不会变成一个封闭的。我说，哦呦，真的耶！那当你想到这件事情的时候，你就发现，哎，那时候想的方法是对的。那我们也发了一篇 paper 就是做这件事情，所以我觉得还蛮有趣的。这世界上的道理好像会连贯在一起。你知道什么叫做封闭的形状吗？封闭的形状就长这样来，就是长这样，哎，这样子就是一个封闭的形状。但如果今天你的形状是这样，然后你的另外一面是打开的，然后这是空的，那这样就是它就不合理哦，它就是不是稳定的状态。我觉得还蛮有趣的。I just talk about a story that when I was studying in PhD, and then I found that my theory can be illustrated by a really simple geometry problem. So sometimes it also means that you are correct because nature will choose a reasonable or simple way to represent in front of you. That's really interesting. Okay, so let's talk about Moore's law. The Moore's law just looks like this. Okay, and it can obtain shear stress, normal stress in any angle. Wow. Okay, so actually the equation you memorized just represent the shear the Moore's law. So remember the formulation. I gave you 3 star, right? And I said this is related to Moore's law. So this is sigma x1 and sigma x1 y1. Sorry, tau x1 y1, and then you do when you do a square and then sum them up together, okay, and then you obtain this stuff, okay. And then if we define sigma average is sigma x plus sigma y divided by 2, and the R is actually what you learned in the geometry, right? The R is this one. And then you can represent this by this one. So this one can be determined here. And then, 5 star. Okay. You notice that actually sigma x1 and tau x1 y1, this one, okay, they are unknown. What is unknown? They actually is a circle formula. You can imagine that this is what you learned in your senior high school, maybe x minus something square plus y square. Is actually this one is the origin of the circle. Okay, and this is r squared, is the radius. So this is actually a circle formula. So when you sum them together, square and then sum them together, it become a circle. Wow. So actually, this is a formulation for a circle at the origin, average, and 0, y, and with the radius r. It's just this one, right? So all the relationship you learned in yesterday can be represented by a circle. So next page, I will lead you step by step to determine how to plot the more circle. More circle. One thing that really important is that actually later I will give you a really important concept, and also this important concept always confuse your senior. I hope it won't confuse you. Okay, you notice that, well, sorry, I need to correct a little bit. This is not, it should be downward. Sorry, the figure is wrong. Okay, so I will give you a concept that tau x1 y1 is downward. I will explain you later. Okay, right. So next page, how to draw a Mohr circle. So again, sigma x and sigma y and tau xy are known, right? We know that before. They are known. Okay, and then we need to draw a really important things here is a how to draw that. Okay, I will give you a think positive downward. Okay, tau x1 y1 is positive downward. So this is really you need to be really careful. Okay, tau x1 y1 is downward and sigma x1 is to the right. So this is the only thing I need you to be really pay your attention on this. Later I will tell you why. All right, and then so you set the point that you set the location of the center C of the Mohr circle. Sigma x1 is sigma average, and tau x1 y1 equal to 0. So, for example, this one is sigma average. Okay, sigma average. And it's at the axis, on the axis sigma x1, because tau x1 y1 equal to 0. So sigma x1 is the name of the x-axis. Tau x1 y1 is the y-axis name, but it's point downward. Okay, so this is the second step. Second step is you locate the center of the circle, and then you can draw the circle as well later. Okay, and then this is interesting. Mark the coordinate point A, sigma x1 equal to sigma x, tau x1 y1 become tau xy. Okay, so now you are going to locate locate the A surface. A surface. And A surface has tau xy sigma x. And the values, this is, you know that, right? You know the value tau xy sigma, tau xy sigma x. So you can get the point here. I assume that the tau xy, and so this is tau xy, tau xy, and this is sigma x. Okay, so we use these two values to locate point A, point A. Okay, and this A specify the tau x, y, and sigma x, which is known, right? And this point represents in the circle world, circle space. This A represent the real world plan. A, okay, and the other point can be B, can be B. All right. Well, this is kind of difficult. Okay, B can be B. Well, you don't need to draw the circle first, but because you know exactly the value of it, so you don't need the circle. But because I want to make it, sorry, I can delete that. I can delete that. Central. Okay, so point B can be set by your tau xy and sigma y as well. Okay, so this is, be careful, here is negative tau xy. Because if you set this if you set this surface as a focus, main surface, this is downward. Downward is negative shear. Okay, but sigma y is still positive, so it's positive in the positive axis. This is sigma y. So now your point B in the circle space represent real world B plan. Okay, so sigma y tau xy, sigma y tau xy, this is minus, and tau xy sigma x tau x. Okay, so you use these three values to locate A and B plan. And then you notice that they are naturally 180 degrees away from each other in the space, a circle space. And then now you're done. You're done. Now you can connect A and B with the circle. Okay. Okay. And then you will notice that the circle with the radius R. Definitely. And then we can say this point A represent the real world theta equal to 0 degree. Because you are representing these surface. And then B point represent this surface, which means that the B is actually represent theta equal to 90 degree. Okay, so that's how you determine draw the a Morse circle. And then if you are going to change your x into x1, and then you can do the rotation of the point by directly solve the geometry problem. Okay? And now I'm going to tell you why tau x1, y1 is going to positive in downward. Because if you go upward, okay, if you go upward, later your rotation of this change of the theta will be completely reversed. So because we want to avoid that, so we change the positive to downward. 好，这边讲一下哈，就是这很重要，就是它是一个特例。为什么要做这件事情呢？因为等一下哈，我们画好这个东西以后，你会发现你的 A 跟 B 是这样差90度，是这样子绕的。你看它真的就是这样子绕，虽然它，然后这边是 theta 90度嘛，但是这边绕的是180度，所以你发现这边有差2倍 ，theta 是差2倍，而且它绕的方向是一样的。但如果今天你的它是往上的话，那就绕的方向是反的，那这样就会有一点会让你们搞不清楚。OK， 就是如果你今天它上面的话，你在现实生活中绕的度数的方向会跟你的圆的方向是反过来的，所以为了避免这样子的纷争，我们一开始就先设定把它往下好，这样子。So because after you see here is a theta equal to 0, this is theta equal to 90 degree. So this is kind of counterclockwise. So you see, this is in the circle space, theta equal to 0 to 90 degree is 2 theta, it's 180 degree in the circle space. So you see, if you go still counterclockwise, so they are smooth. But if you they are straightforward. If you change this to here, the rotation will different from the real space. So that's the reason why I set positive downward for the tau x1, y1 axis. Okay, this is really important. So now we set the Morse law. Now we are going to use that. We are going to set the theta 0. Okay, if we make the x1 theta 0, and then we said this is D plan, new axis, x1. So we are going to determine sigma x1, tau x1, y1. So where is D? Now we know this is theta equal to 0, theta 90 degree. So which means that it starts from theta 0 to theta 0. Sorry, 0 degree to theta 0. Okay, so 0 degree rotate to theta 0, theta 0, you need to double it. Okay, in the circle space. So here is D, and which means that the theta equal to theta 0, but it should 2 theta 0 in the circle space. Now you set the D point. Now, all you need to do is just get the coordinate of this D, and then you can get to the sigma x1, y1. Sorry, sigma x1, tau x1, y1. So this is what you want to get, sigma x1. And this is what you want to get, tau x1, y1. So now it transformed the problem, stress problem, into a triangle problem, circle geometry problem. It will be really easy. Even junior high school student can solve this problem, right? Then, interestingly, if you set this this we call D plan. Okay, we call D plan. D plan is 90-degree rotate from the brown plan D. So in the circle, it will naturally rotate 180-degree. So this is D plan. And of course, this is theta equal to theta 0 plus 90-degree. Okay? And of course, it start here from 2 theta 0. Okay? And that is negative tau x1 y1. And this is sigma y1. Okay? So that's how you get the value. That's how you get the value. Okay? Not difficult at all. And next, I'm going to introduce that the Mohr circle can also help you to get the principal stress and maximum or minimum normal stress. So now you see the value, you see the circle. Where is the principal stress occurred? Here and there, right? So your normal stress, sigma x1, has your maxima here, minima here, right? So it will make you to lead you to the next page. Next page is that going to introduce principal stress. The principal stress can give you this one, sigma 1, and this one is sigma 2. And remember that this one center is sigma average, right? Equal to sigma x plus sigma y divided by 2. You can see that this is R. This is R. Don't you think this is sigma average plus R, sigma 1? Average minus R, sigma 2. So now you know where sigma 1 and sigma 2. And this is 2 theta P. So everything is here. Everything is in the circle. Okay? And you can do exactly the same thing for shear. Okay, I will finish this today and I will see you next week. Next week, Tuesday, we will first give you the quiz and then we will continue our lecture. Okay? That's it. Thank you. If you have any questions, come here. Bye-bye.